Okay, so now that we know what the regular functions are, the big result in this video here will be calculating them on these distinguished open sets. And so let's say R is a ring and F is in R, and we have this distinguished open set dF. We can look at the regular functions, and the claim here is the regular functions are exactly given by the localization of R at the element F. And the map giving the isomorphism, the map big phi, just takes some element of the localization, so G divided by some power of F, and gets this family. Remember, function here is a family of elements in these localizations at all the prime ideals here. And you just take, well, the same quotient G divided by F to the M at all of these prime ideals. And again, P is in dF, just means that F is not in P, so F to the M is something that we're allowed to divide by. And the claim of the proposition is this map here is an isomorphism. In particular, if you take F equals to 1, then O of spec R of D of 1, the set of prime ideals not containing 1 is everything, so it's all of spec R. And this is exactly given by R localized at 1, which is just isomorphic to R. So we get this property that we wanted. And so if you remember in the last video, we said the ring of functions should satisfy 3 properties. It should give R on all of spec R. It should give RF on DF, and it should be a sheaf. And with this proposition, we have checked the last property that it gives the right thing on this DF. Okay. And now this video will just be a long proof. And I mean, it will be somewhat technical. So if you like, you can now actually go back, instead of just watching the video like this, you can go back to the affine varieties part where we discussed the corresponding property. And the proof will be very similar. In particular, the surjectivity part will be very similar. And you can just try to watch that video and then in parallel write down, for example, the surjectivity part and try to see that everything just matches one-to-one what we did there. For the injectivity part, there is one additional idea that you need to have. Okay. So let's just get started with this big proof. So we showed this map is an isomorphism by first showing it's injective and then showing it's surjective. So for the injectivity part, let's say we had something which is in the kernel. So let's say G divided by F to the M is in the kernel of big phi. So in other words, this G divided by F to the M, all of these entries should all be 0. So these should be 0 in RP for all P in DF. And so, by definition of RP, what does it mean to be 0 in there? It means not necessarily that G is 0 in R, but that if we multiply by some element of the multiplicative set, then we can make it 0. So in other words, there exists HP in R minus P, an element of the multiplicative set at which we localize such that G times HP is equal to 0 in R. Let's call this thing, I think I want to call it like this. Okay, so then we need to show that this thing was 0 in the domain here. So in other words, we can multiply by some power of F such that we can get 0. So in other words, there exists R in N such that F to the R times G is equal to 0. And so at this point, if you just try naively, it's not so clear how do you go from this statement to this statement here. And the crucial extra idea here is to reformulate this as saying, so here you see these are things of the form, you have some elements in R which multiply to G give 0. And there's a name for this. So you can call J the ideal, which is the annihilator in R of G. So this is the set of all H in R, such that H times G is equal to 0 in R. And then with this language, it makes sense to say, to reformulate this thing and saying, what we just want is that some power of F is in the annihilator. Is in here. And the good thing is that this here also makes sense, because then this HP is in the annihilator for all of these elements. And how do you prove this? We prove an intermediate claim, namely the claim that we really want to prove now to finish the injectivity is that if you look at the vanishing locus of this J, it is contained in the vanishing locus of F. So somehow the fact that we had some power here told us that maybe there will be a Nullsternsatz involved. And in fact, if you think about it for a second, this claim here immediately implies by the Nullsternsatz the claim that we want and finishes the injectivity. Because if you have this and then you apply the vanishing ideal on both sides, then you get the vanishing ideal here. So in other words, the radical of the ideal generated by F is contained in the radical of J. In other words, F is in the radical of J, so some power of F is in J. Okay. And so we just need to prove this claim. And this is basically just some manipulation of the definitions of the vanishing loci and of basic logic. So somehow the vanishing locus of J is, this is just spelling out what we already know about the definition, is the elements of spec R such that P contains J. And then for any P in DF, this star here, I claim, the star implies that HP is in J, right? This is the observation I did before. HP multiplied by G is 0, so HP is in J. But also by the definition, this HP is not in P. And so, in other words, HP is an element of J, which is not contained in P. So in other words, J is not a subset of P. We find an element in J which is not in P. And then this implies, by definition, that P is not contained in Bj. And then we're basically done, because this means df is contained in the complement of V of J, because we have shown for any P in df, P is not in Bj. So in other words, df must be in the complement of Bj. And then if you again take the complement in spec R, you get that V of F complement reverses the inclusion contains V of J. Okay. So I admit this last part, there were some things which seemed to fall out of thin air, but in fact, well, if you start with this and then start expanding what it means, then you can kind of reverse engineer how we got exactly this sequence of things. But also, I mean, if you want, you can just follow kind of line by line what is happening. But here, if you go back to the affine varieties video, this part of the proof is actually much easier. The injectivity is just kind of 2 lines. And here, this is one place where the scheme theoretic treatment makes things a bit more complicated. But again, in the end, it was all just basic definitions. What is the vanishing set and so on. Okay. So this is the injectivity. And now the surjectivity, this is a bit longer, but this is very similar to the treatment that we had before. So for surjectivity, we need to start with something in the image of the map, and then we need to show it comes from something in the domain. And so the first observation, so let's give ourselves any phi, which is a section on df, defined every branch. And then this means that for any point in df, we have this local form of this local condition. So in other words, for all p in df, there exists. So first of all, we would say we find this green thing, this up, on which this is given by some quotient. So we would write phi equals gp divided by fp. And a priori, this would be on up, like this. But we already want to reduce everything to elements of the ring. And so we can find the basis element of the basis of this Zariski topology DHP, some distinguished open, inside UP. So in other words, we only want this thing here on DHP. So in other words, we want to find this HP in R, such that P is of course contained in DHP, and such that this here makes sense. And well, it should make sense. So in other words, we want that FP is not equal, not in Q for all Q in DHP. So this is the first form that we can find. Let's already observe this here is equivalent to saying that for all Q in here, this is not contained. In other words, Q is contained in D of FP. Okay? And so we have that D of HP is contained in D of FP. So somehow now we have written this phi locally around each point as such a quotient. And the whole rest of the proof is manipulating this form in which we can put the phi and making it kind of easier and easier. And so the first claim is that we can assume that FP is equal to HP. Okay. So before we have here an HP and an FP separate, and now we want to make them equal. In other words, by choosing, by modifying the representation that we have here to make this happen. And so this observation that we have made here is that DHP is contained in D of FP. Now it's always kind of the same spiel. So we take the complement and we have V of HP contains V of FP. And then what do we do next? Think about for a second. Well, we apply the ideal on both sides. And then we get that by Nullstellensatz, this thing here is contained in this thing here. And at that point, we always observe that HP is, of course, contained in its own radical. And so spelling this out, we have HP to some power R is some multiple of FP. So it's contained in the ideal. Yeah. And then the idea is we had this representation of phi as GP divided by FP. And then the claim is where we can replace the denominator by HP to the power R. And then if you check what you need to do because of this, because they differ by a factor C, you need to have an extra factor C here. So basically just multiply it out and then you see this. Okay. And so the phi was given by this thing, and now we just replace the old GP by this C times GP. This is the new GP. And this thing here is the new FP is HP to the power R. And we observe that D of HP to the power R is the same thing as D of HP. This also follows because a prime ideal contains HP to the R if and only if it contains HP. And so we choose the new GP to be this, the new FP to be this, and the new HP we can now also choose to be this, because it doesn't change the set. And what this has done for us is that now the D of F is covered by these open sets DFP. For each point P, we have this thing, and phi, the thing that we started with, is given by this quotient GP divided by FP on here. Okay, and now the next thing that we introduce is this lemma of this partition of unity that we had before. That's the reason why we proved it, because remember this said that if some df is covered by dfi, then we find a finite subset and these coefficients such that we can write f to the m as some linear combination like this. And this is exactly the situation that we have. The dfp, the df is now covered by this dfp. And so from the lemma, it follows that we can write f to the power m as some linear combination of rp times fp, where this now becomes a finite sum. Okay. So until now, we have just treated every point p separately and manipulated this representation here. But now, of course, what we need to use is that all of these representations glue to the same function. So in other words, on the overlaps, so on d of fp intersected d of fq, which, as before, is just the same thing as the fp-fq, we have that these two representations both give the same function phi. So, and this is an equality in O spec R of d fp-fq for all p and q. And then now we actually use the part of the statement that we have already proven, I mean the injectivity. Shows, you see, these two are elements here which come from this localization R, fp, fq. So this is basically phi of this element and phi of this element agree in this thing of sections, and then by the injectivity they must have agreed before applying the phi. So in other words, this GP divided by FP is equal to GQ divided by FQ as elements here. Okay. And so spelling this out, this means that, I mean, it almost means that this GP times FQ minus GQ times FP is equal to 0 in R, but only almost, because what you always have to do is multiply by some power, yeah, like this. So this now works for all P and Q appearing as indices in this finite sum. And so because it's a finite sum, so a priori, for each P and Q, you would choose a separate power here, a separate NQ. But in fact, since it's only finitely many such pairs, you can pick an N which works for all P and Q in the finite sum. Okay. And now, since we don't always want to drag around this, this strange compatibility here, what we can actually do is we can replace our choices above, namely the new GP. We just extend numerator and denominator by the same element, namely we extend it by fp to the power n, and fp then becomes fp to the power n plus 1. Just in this representation, multiply by fp to the power n on both sides. The good thing what this does for us is that then you see this equality here, then you see here an fp to the n times gp and an fq to the n times fq. So you see, if you multiply this here in, then you exactly get these new numerators and denominators. And so what this tells you is that instead of this weird compatibility, you actually just have a compatibility on the nose. The product of these new numerators and denominators is equal to this thing here. So this df is now covered by these finitely many dfp with this representation here, such that these and these agree for all elements in this finite sum. Actually, you don't really need to show that these subthings here cover. You can actually just say this is covered by all of these things, and you just know this equality here for all the fp appearing in the finite sum. Yeah. And so we're almost done to the final thing, because now what we write down, we wanted to prove a surjectivity statement, and now we can actually write down which element maps to this phi. So we can write down the pre-image. So to conclude, we have already seen this thing here. Yeah, let me maybe yeah, let me replace let me take this notation. So f to the m is equal to this combination of rp times fp, as before, finite sum. We set g to be these rp, and now times, we take the gp instead of the fp. And then we check an equality. So we want to check, let me write it like this. We want to check that g divided by f to the m is equal to this gq divided by fq on d of fq. So we want, this would prove that phi is equal to big phi applied to g divided by f to the m. This would prove this. So somehow this would show that this here is exactly the pre-image that we want. So for this, we need to check that this equality here holds. And then what we just do is we write this thing here out and check that it is true after we clear denominators. So in other words, if we take, sorry, this should be an FQ. So if we take G times FQ, then we insert the definition. We insert the definition of G, and now we can apply this thing here, and we get GP times FQ is equal to GQ times FP. But now the sum of RP times FP, you can draw out the GQ. We can draw out this GQ. And then what is left, the sum of RP times FP is just the F to the power M. And this works for RQ. And so you see, this is just exactly what you get for multiplying this thing out. And then this thing here works. And I guess in order to apply this star, you actually do need to check that the df is covered by these finitely many dfq. But this follows from the fact that the f to the m can be written as such a sum here, because if you're then with this you can show if you're in the if you're in the vanishing locus of all of these fp, and you're also in the vanishing locus of this f to the m. Okay. So this was the proof. We can make a proof sign. And so we have checked that the regular functions on the f are exactly what we expect. It's the localization of R at f. And this is often more useful for calculating the regular functions on some open set than the actual definition. Okay, that's everything for this video. And then we're going to continue next time.